Control L. Hello, my name is Ali Farahat. I'm from Michigan Technological University and will be presenting our paper with Ali ibn Nasser, local reasoning for global convergence of parameterized rings. We'll start by defining what convergence is and our model of computation, and why designing in the global state space is complex. Will motivate then our local reasoning for both deadlocks and livelocks, and based on the results we have about local deadlocks and livelocks, we'll explain a methodology to design convergence. We'll summarize our work and give a preview of the related work. We start by our definitions. Self-stabilization is the ability of a system to resume its legal behavior in a finite number of steps regardless of the initial state, and this property we call convergence. And it has the property that we call closure, and closure means that once the system is an initial state, it remains so. We can visualize the state space of a protocol by partitioning it into green states, which are the set of legitimate states, and yellow states. And in a stabilizing system we should have computations or path going from every yellow state to some green state, and we shouldn't have any arcs or transitions getting us from a green state to a yellow state. And these red arcs are actually transient faults, and they are not executed by the dynamic systems, they are executed by the environment. And we should, if we have a stabilizing system, we guarantee that with no transient faults we'll always get to a green state and remain there. Our aim is to resolve all the deadlocks outside the set of legitimate states. So what is deadlock? A deadlock is a global state where we have no outgoing transition. There is no way to go. So we shouldn't have these in a stabilizing protocol. Moreover, we shouldn't have any cycles in the yellow states. So we should avoid both of these. We represent protocols by sets of variables, sets of processes, and read and write restrictions that tell us which process reads which variables and which process writes which variables. A global state is evaluation of every variable in the protocol, and a local state is evaluation of only the readable variables of the protocol. And as we can see here, these are the variables readable by pk-2, and this is a local state of pk-2. A global transition is a pair of global states. So this is a global transition, a pair of global states, and it actually captures the effect of processes writing variables. Maybe one, maybe many processes, and they can cause or exhibit a global transition. A local transition actually captures the effect of one process modifying its local state, and the process can modify its local state by writing the variable, one of the variables that it can write. So a restriction on a local transition is to keep all the variables that are not writable unchanged. A local transition of any process, let's say a process pi, corresponds to a group of global transitions that keep the unwritable variables unchanged. It means that for every local transition we could have a set, we actually have a set of global transitions, because the variables that we can't read, that a process can't read, could evaluate to any value, and each valuation of these unreadable variables corresponds to a specific global transition. This is a representation of the state space, of the global state space of a token ring protocol that has only 3 variables and 3 processes, and we can see the groups here. So for example, these 3 global transitions represent a group of a specific local transition that reads 1 for x0 and x2, and 1 for both of them, and writes 2 to x0 and leaves x2 unchanged. And of course here we have x1 unreadable for this local transition. That's why we have a group. And you see, this is just for 3 processes and 3 variables. Actually, the design is complex because of the state explosion problem. Every time we add a variable, the size of the state space is multiplied by the size of the domain of the added variable. So it is an exponential growth. Our problem is actually given a non-stabilizing protocol and a set of legitimate states. We need to algorithmically add local transitions for each process such that the protocol that we obtain is stabilizing. So we are actually adding convergence without violating closure, and we are not adding any local transitions inside the set of legitimate states. So we need to resolve these deadlocks, but the problem is that in the global state space, due to grouping, we could be resolving deadlocks while forming non-progress cycles, because by adding local transitions we actually add sets or groups of global transitions, and this actually makes the problem more complex because we need to consider a combinatorial number of possibilities to have a stabilizing protocol. What we thought about is that, okay, let's do it in the local state space. Our objective is to mitigate both state explosion and the grouping. So when we do local reasoning, we don't have any groups because we are thinking locally, and we don't have state explosion because we are just considering one process. So regardless of the number of processes we have in the network, we just consider the state space of a local process. Here is the state space of a process in a unidirectional ring, and here the ring size is k. It means we have k processes. Every process reads a variable xr and the variable xr minus 1 of its predecessor process and writes its own variable xr. These are all the possible valuations of xr and xr minus 1, and we have only 9 states in here. So for example, if we consider an agreement protocol, locally in an agreement protocol, every variable xr should be equal to its predecessor's variable xr minus 1, and this is for process pr. So we can locally verify that the process is in a local legitimate state. So the notion of a local legitimate state is possible to define here, since we have locally conjunctive sets of legitimate states, and we'll keep this for the rest of our presentation. Let's see. Okay, now if we consider deadlocks, we want to resolve every local, every white state need to have an outgoing local transition. But is that the case? I mean, do we need to resolve every white state not to have global deadlocks? The answer is not necessarily. It turns out that just by resolving these 3 local states, we don't even need to add local transitions for these white states, and we will not have any global deadlocks even though we have local deadlocks. And that's actually interesting. But why is that? We need first to define what we call the continuation relation, and the continuation relation it is a binary relation between local states of neighboring processes. So 2 local states are in the continuation relation, so SR is related to SU if the local state SR has a variable that the writable variable in this local state is readable in the process that is in the state SU. So for sure X, this writable variable, is of SR is the same as of SU. So if we consider a diamond topology that has only 4 processes, just for illustration purposes, and we have 4 variables, each of them are binary, so we have just binary domains. This process P0 can only be in 0 or 1. This is the local state of process P0. P1 and P2 have 4 local states, and P3 has 8 local states. So if we want to define the continuation relation between every pair of neighboring processes, for example, here 1 is connected to 1, 0, because here x0 equals 1, and in P1 x0 equals 1 and x1 equals 0. So they have the same value for x0. So these two states can be in the same global state simultaneously. The idea is to represent a global state using how the topology looks like. So a global state actually in the continuation relation is represented by a diamond, and the thing is that we can't choose an arbitrary local state in each process and say that okay, this will form a global state. No, that's not the case. They should all be in the continuation relation. They should all be forming a diamond. So the only global states we can form are those along the diamonds. This is we can use this in the following way. A deadlock is actually a global deadlock. Has every local state in a global deadlock is a local deadlock. It means every local state has no outgoing local transitions, and at the same time it suffices to have only one white state in a global state for it to be illegitimate, because we assume locally conjunctive predicates. So the state 0, 1, 0, 0 is actually illegitimate, and it has at least one white local state. So if every global state in here is a local deadlock, this is a global deadlock. So if we have diamonds over sets of local deadlocks, it means that these diamonds are global deadlocks. And if they have white states, it means that they are illegitimate global deadlocks, which is a nice way to reason about deadlocks just by checking the geometry of the continuation relation. So for rings, the situation is even better, because if the ring is symmetric, it means that every process has the same actions as its neighbor. So they have the same set of local deadlocks and the same set of local legitimate states. All we need to look for is a cycle in the local continuation relation. So if we could find a cycle over these deadlocks, then it means that this is a global deadlock. So we need to only consider the continuation relation over local deadlocks. So this is, for example, this is a ring of size 6, and this is a global deadlock if every state in it is actually a deadlock. But if we start resolving states, we'll be getting rid of deadlocks, and then we are getting rid of cycles in this graph until we reach an acyclic graph. Here we resolved only two local states and we have this cycle. If we resolve this remaining state, we don't have any cycles, yet we still have local deadlocks. Well, still having local deadlocks, but there is no way to form a global deadlock. There is no way to form a global deadlock, even though we have local deadlocks. So here is the theorem that we have in the paper for deadlocks. A symmetric ring is deadlock free for every size of the ring, if and only if the continuation subgraph of a representative process over local deadlocks has no cycles through illegitimate local states. It means that it has no cycle through white states. And we applied this to a maximal matching protocol, and here the set of legitimate states is such that every pair of processes match through their values. So if a process had a value right, its right process should have the value left. This is a matching. So we had actually two solutions. We verified two of them. One of them has this induced continuation relation. Of course, these protocols are symmetric. This is an induced continuation relation over local deadlocks. The only cycles we have here are among legitimate local states, which means that we are fine. We don't have any white states in the cycles, so we will not have any deadlocks that are outside the set of legitimate states. So this protocol has no deadlocks for any size of the ring. On the other hand, if we consider this is another protocol, it works for some sizes. For other sizes it has deadlocks. For example, it has a cycle here with a white state, and this cycle has a size 4. And we can form rings of size 4, 8, 12, and all multiples of 4. And these rings are in global deadlocks because they have an global illegitimate deadlocks because they have the local state. One of the processes will have the local state LLS, which means that a process is in left, its left is in left, and its right is in self, and they don't have, there is no outgoing local global transitions from this state. So this is how we reason about deadlocks. So what about livelocks? First we have to assume self-disablement, and we say that a process is self-disabling if and only if the target local state of every local transition is a local deadlock. It means that there is no way, after the execution of a local transition, there is no way that this process executes anymore unless it is enabled by its predecessor. And here we talk about unidirectional rings, livelocks in unidirectional rings. For example, this is not a self-disabling process, because if this local transition executes, we are still in a local state that is enabled, and we are not considering such types of protocols for livelock analysis. Since we have self-disablement, we could consider any execution as a propagation of enablements along the arcs of the unidirectional ring. That's because any process that executes will get disabled. So, for example, we are here in process 3 is in state 0, 0. When it executes, it goes to a state 0, 1, but it's already disabled. There is no outgoing transition here. And P4 actually gets enabled. So, as we can see, P4 gets enabled. And whenever it executes, well, it goes to 1, 2, but P5 doesn't get enabled. It's still disabled. Actually, here is the local state of P5, and it has no outgoing transitions. So, we are faced with the following situation for self-disabling processes in unidirectional rings. A computation or an execution can be seen as propagation of enablements, and the number of enablements never increases. It either remains the same or decreases. And one other reason for decreasing is what we call a collision. So if this process executes, it will lose its enablement, and its successor it lost its enablement too. So the number of enablements in the ring during any computation either remains the same, decreases by 1, or decreases by 2 at most, if just one process executes at a time. So this has a very important implication, because in a livelock we can't have if the number of enablements decreases, then it cannot increase back. So this can't be a livelock. This can be a global state in a livelock, because this global state will never happen again. So we have this main theorem for livelocks that says that a unidirectional ring has a livelock if and only if every global state in the livelock has the same number of enabled processes or the same number of enablements. So we can think of a livelock on a unidirectional ring of self-disabling processes as a propagation of a fixed number of enablements. And this is actually the case. So let's consider a livelock with 3 enablements for a coloring protocol. So in a coloring protocol, every variable shouldn't be equal to its predecessor. So it's different from the agreement protocol. So it tries always to escape when both variables have the same value. So what happens then? It has a livelock. Here we have a livelock. So if P2 executes, it keeps propagating the enablement. One interesting thing is that we don't need is that the order of execution of local transitions in a livelock does not really matter, as long as we don't have any collisions, and the order does not really matter. So for example, if we execute the local transition T0 in the process P1 in this livelock, and then execute the local transition T2 in process P4, it doesn't matter which one executed first. In fact, we don't need to consider all the set of livelocks in a protocol. We need only to consider what we call a representative livelock. This is a partial order invariance property or a partial order reduction. So we can only consider what we call contiguous livelocks. A contiguous livelock has a propagation of the topmost enablement until it reaches the tail, and then it keeps going in this way. So we can just focus our search for livelocks locally to contiguous livelocks. So we don't, because if we have a livelock, we should have a contiguous livelock in a unidirectional range, and vice versa is trivial. I mean, the converse is trivial. Now we are looking for livelocks in the local state space. How we can detect these livelocks locally? How we can detect these contiguous livelocks locally? First, we define what we call the pseudo livelocks. So it's the projection of a livelock on the writable variables of a process. So if we do the projection, we just consider this. It should be a cyclic behavior. I mean, if you have a livelock, you should have a pseudo livelock. So first of all, every process in the network should be in a pseudo livelock. That's the first condition for having a livelock. This is a necessary condition for having a livelock. And then we need to consider this pseudo livelock. So for example, these three local transitions in a coloring protocol are in a pseudo livelock because they form a cyclic execution on the variable xr. So we need to consider if we have any contiguous, we need to detect this contiguous livelock. So we'll have this contiguous livelock in the following way. So the contiguous livelock just is a propagation of this rightmost enablement. So this transition keeps like executing, and now we are in, as you can see, it's an alternation of a T transition and a continuation transition, or an S transition. These arcs are from the continuation relation, and after reaching this, we need to go through the enablements. We have three enablements, so this is one of them, and this is the second, and then we will we'll repeat again the execution. So a contiguous livelock, or a contiguous livelock, is detectable by a contiguous trail. That is an alternation of T and continuation arcs, and then it could have like a fixed number of S arcs before restarting this this trail again. We call this a contiguous trail. Okay, now we go to the algorithmic design of convergence. We need to be eliminating deadlocks, so we need to choose a set. Here we consider a different protocol that we call the sum not to protocol. So the sum of the variable and its predecessor is not 2, and all we need to do is to add transition or to resolve deadlocks in such a way that we don't have any cycles. It means that we are looking for a minimal feedback set of the continuation graph. It turns out that in this case we have to resolve all the three white states. Unfortunately, I mean, in this case we can't keep any of the local deadlocks, so we have to resolve all of them because all of them are forming independent cycles. So we have to resolve all of them, but the question is how to resolve them such that we don't get any livelocks. So these are all the possibilities of resolving these states without getting any without having deadlocks. But how do livelocks form? We need to look for this contiguous trail. So if we have the contiguous trail, then we are not certain, we don't know if we have a livelock or not. But if we don't have it, we are sure that we don't have this livelock. So for example, here we augmented the relation with the continuation graph to be looking for the contiguous trails, and we'll consider this pseudo livelock. So here is a pseudo livelock of three local transitions, and as you can see, we are forming the trail here. So it goes one transition with two continuations, and then one transition with two red continuations, and then one transitions with two continuations. So actually we do have a trail. So we don't know if this forms a livelock or not. So, but we should discard this subset. We'll be looking for another subset now. This subset has a pseudo livelock in here, and we need to see if it forms any trails. Interestingly enough, it doesn't form any trails. So it means that for sure, if we include these three transitions to resolve the deadlocks, we will not form any livelocks globally. So to summarize the design, we choose a minimal feedback subset of local states to resolve, and this is and then we look for transitions to use in order to use and resolve these local deadlocks, and make sure that these transitions either don't form pseudo livelocks, and if this is inevitable, if they form pseudo livelocks, then make sure that they don't form a trail. But if they do, if all of the possible subsets of local transitions do form a trail, then we can't avoid anything. I mean, we can't say anything about it. So this is just the related work about regular model checking, and it's work about network grammars. So networks are formed using grammars, and this is the approach of Stadler and Grunberg, and we can't use this for design. It becomes like very complex. As for verification using cutoff sizes, we are not sure how we can use this approach for design, but these approaches are pretty good approaches for verification. We conclude that verification and design of convergence in the global state space suffer from state explosion and combinatorial choices. That's why we are using the local reasoning approach. For convergence, we need to reason about local deadlocks and local livelocks. We presented necessary and sufficient conditions for deadlock freedom in rings that are possibly extendable for other topologies. As for livelocks, we presented sufficient conditions for livelock freedom in unidirectional rings that could be checked locally, and we provided a methodology for the design of convergence. The future work, we already submitted a paper to DISC for necessary and sufficient conditions for livelock freedom in unidirectional ring that are self-disabling processes. We need to extend the local reasoning for arbitrary network, devise algorithms and tools for the design of convergence in the local state space, investigate local reasoning about reachability, and relax the self-disabling constraint. And that's it, and thank you very much for your time. Waiting for your questions.